All right, so we were doing this example. I introduced this idea of input impedance being the voltage as a function of position divided by the current as a function of position. And then I asked you to think about what is the input impedance of a quarter wavelength transmission line that's terminated with a short circuit. And then if you got that one, you're supposed to think about what if it's an open circuit. I think a lot of groups were confused by it, so I'm going to talk through this and help it make sense. Because it's weird. It's really weird, but this is what we have to understand today. So here's our transmission line. Of length, whoops, that's not how you draw length at all, of length L, and it is terminated by a short circuit. So this load impedance in this equation works out to be 0. What's our reflection coefficient here? If you want to work that out and somebody tell me what the reflection coefficient is, just type it in the chat. So if I evaluate this, what do I get?
-1.
Yeah, so I get a -1 here. And if I write my voltage equation, then voltage as a function of position, and reminder, this L is just because Z is defined to be 0 at the position of the load. So any values of Z to the left of the load are negative. We don't really, that's weird to give it a negative length because Z is going positive towards the load. So we define this new variable L that is minus Z, right? So just L equals minus Z. And it's just the length of transmission line that we're interested in measured away from the load going back towards the generator, which we're not thinking about right now. So voltage as a position of L is going to be whatever our forward going voltage amplitude was times e to the plus j beta L plus that reflection coefficient, which is -1. So minus e to the minus j beta L. Well, that just looks like a sine, right? So that's 2 V0 sine of beta L with a j, right? Because of our Euler's identity stuff. If I do the same thing for current, that's not how you write the letter I. There you go. It's going to be that same voltage amplitude divided by Z0, and then our forward going wave has e to the plus j beta L minus gamma, which is -1, so that gets me a +1, e to the minus j beta L, like that. So for this, I'm going to get 2 V0 over Z0 cosine of beta L. If I plot these two, and remember that both of these are phasors, so if I want to convert them back into the time domain, what I have to do is multiply by e to the j omega t and then take the real part of the whole thing. Same thing here. So you find that there's this amplitude part that depends on position but not time, and also a time varying part. So I'm gonna erase this for now and then plot them. And then we'll go back to the input impedance equation and show you that you get the same answer that way. So if I plot the absolute value of this voltage, the reason I'm plotting the absolute value is because see this e to the j omega t? That means that this is always cycling through time, right? It's going to go, this value is going to go from a -1 to a +1 and through all of the complex values in between. So when I'm talking about the amplitude of this voltage, it only really makes sense to talk about a positive amplitude. So usually when you're plotting the standing wave, you plot its positive amplitude. And we're still working in phasor domain, so we're not going to worry about that e to the j omega t. So here, if I put my load here, let's say L equals, well, I drew the arrow to the right, so that's Z equals 0. Let's plot what happens at, I'm going to use L. L equals 0, L equals lambda over 4, lambda over 2, 3 lambda over 4, and that ought to be enough to get you the pattern. Right? So sine of 0 gets me 0, so that's my 0 point. Sine of 2 pi over lambda times lambda over 4 gets me sine of pi over 2. Sine has a maximum of pi over 2, so I got a maximum value there. And that maximum value, ooh, a little too high, is 2v naught. And then at the next point, half a wavelength, 2 pi over lambda times lambda over 2, that gets me pi. Sine of pi is 0, so I got another 0 point there. Then 3 lambda over 4, let's see, 2 pi over lambda times 3 lambda over 4 gets me a 3 pi over 2. Sine of that would be -1, but we're taking the absolute value, so that's another maximum. So my standing wave of voltage looks like this. When I plot the current, if I do the same thing, but I have a cosine of beta L. So at 0, that's going to have a maximum. And that max value, I'm just going to label it over here, is 2v naught over z naught. So it's got some max current value. That's that. All right, so what about at a quarter wavelength? Well, then we've got 2 pi over lambda times lambda over 4. So that's a pi over 2. Cosine of pi over 2 is 0. So I got a 0 there. At the next value, lambda over 2, it's more like that. I've got 2 pi over lambda, lambda over 2. I get pi. Cosine of pi is -1, but we're taking the absolute value, so that's a max. And then over here, I'm going to get another 0 for the same reason. 3 lambda over 4 gets me 3 pi over 2. Cosine of 3 pi over 2 is also 0. So my current standing wave looks like this. So let's take a look right here at the load. If I divide the voltage by the current, I get 0. So V of 0 divided by I of 0 is 0. That makes sense. That's the load impedance. The load impedance is a short circuit. We get 0 there. Let's move a quarter wavelength away from the load towards the generator. Okay, right over here. Let's look at it here. Now we have a voltage maximum and a current minimum. We have voltage of a quarter wavelength divided by current at a quarter wavelength. Well, that's some finite value divided by 0, so that goes to infinity. We have an open circuit here, right? So this is a short circuit, but a quarter wavelength away, the input impedance looks like an open circuit. That's pretty weird, but that's how it is. And it's because these two standing waves are not necessarily lined up with each other. The reason that they're not lined up with each other is because take a look at the phases on these two exponents right here at the bottom. This one is accumulating positive phase. This one is accumulating negative phase. So I could also write this, I could divide through, and then I could have 1 minus gamma L e to the minus 2j beta L. And then we'd be talking about this is the relative phase between the forward going and backward going waves. So they have this opposite phase relationship to each other as they're going past. Sometimes we talk about a reflection coefficient that is a function of position, right? We could write gamma of L is equal to gamma L e to the minus 2j beta L. And that is just what is the relationship between the forward going voltage wave or current wave and the backward going voltage or current wave at a specific position L, rather than only talking about it at the load. All right, so let's put this whole plot back into the context of input impedance. I'm going to draw a plot of input impedance for the same thing. So L equals 0. I got to compress it a little bit. Lambda over 4, lambda over 2, lambda over 3 lambda over 4. There we go. If you remember, there was a J. The voltage was 2 V naught J sine of beta L, and the current was 2 V naught over Z naught cosine of beta L. So I could just divide these two things, right? So if you were in a group who worked out using that equation and figured out that the input impedance to a short circuit, to a transmission line terminated with a short circuit, is J tangent beta L times Z naught, you were right. And we can also figure that out from this very plot, right? Here we've got 0 voltage divided by finite value current. We're going to get a 0 there. Here, and we're going to plot the imaginary part of Z in, because we know from this that it's purely imaginary. And you will find that in general, if you are not delivering power to a load, the input impedance is purely imaginary, or it's 0 or infinity. You can't deliver power to those things. So if you have a purely reactive load, if you have a short circuit, if you have an open circuit, your input impedance is always going to go through a standing wave that looks like this. It goes all the way to 0 and all the way to 2 times the incident amplitude. It's just going to be the position of those things that are offset by the phase that you have at the load. So anyway, when we divide this large positive voltage by 0, it's going to go up, right? So like that. We have another 0 at half wavelength, and then it goes down and then up again like that. So our input impedance at this thing, since it's a perfect short circuit, looks like a plot of a tangent, which you have seen before. And that agrees with the actual equation that we have, which is Z naught times ZL plus J Z naught tangent beta L divided by Z naught plus J ZL tangent beta L. It all comes down to what these two standing waves are doing and how they're related to each other. This has been a lot. This is a lot to hold in your head. It's not super intuitive. Why are the voltage and current changing with position? It's not awesome. And then this idea that their phase, the relative phase of these two waves changes, that's also kind of weird. It's hard to visualize. Luckily, we have a tool whose entire job is to help you visualize it, and it is called the Smith chart. I don't even need to erase this because I can just put this on the floor and put a Smith chart on my desk.
Professor, could I ask a quick question?
Yeah, absolutely.
So those last graphs, the ones you just erased, the lambda over, like 4 or 1 or whatever, those stand for the position relative to the wavelength along the line, or do they stand for the standing wave that we're giving it?
Relative to the wavelength along the transmission line.
Okay, so like for the question that you asked in the breakout room, because you were just concerned about one quarter the wavelength, what position were you kind of asking for? I guess. If it's a long answer, I can ask it another time. I don't want to take up too much class time.
What I was asking for is you have a short circuit here, and it's connected to the end of a transmission line, and this transmission line is half of the wavelength on the transmission line long. The wavelength on the transmission line is not equal to the period of the standing wave because of that absolute value function and because of the fact that the two waves accumulate phase in opposite directions. The period of the standing wave is actually half the wavelength, not the full wavelength. Right? But we still have a forward going wave like V plus as a function of Z. Can you see if I write this?
Do I need to zoom in? Okay. I can see it. Fine.
So V plus as a function of Z is going to be some amplitude times e to the minus j beta z, where beta is 2 pi divided by the wavelength, or it is omega square root of L prime C prime, the per unit length inductance and capacitance, or it is omega square root of mu times epsilon, the material constants of the transmission line. All of these things are equal to each other, and this sets the behavior of the transmission line in a bit. So once you know these material constants, or you know these per unit length inductance and capacitance, you can get the wavelength, and it is a property of the transmission line that we're kind of stuck with. And so a lot of the time we specify the length of a transmission line in wavelengths.
And you just want to find the input impedance at the totals.
Right. So if we give it this length, and we want to know the input impedance there, then that means that we want to know what is V of that position divided by I of that position. And that's actually like Z equals minus L, because again, Z is positive going to the right.
So those graphs that you drew were showing V and I as the length changes?
Yep.
Okay, it was because that where the wave changes and where the length changes, that was confusing me, but I think I get it now.
What do you mean where the wave changes?
I guess I was getting length and wavelength. I was sort of mixing, I wasn't understanding them properly. I was mixing them up in some way.
Okay. Yeah, I was drawing this scenario, and then I was allowing this value of the length to be a variable so that we were looking at the input impedance at like different positions along the transmission line.
Positions which are relative to the wavelength, as you said. Okay.
Yeah, exactly.
Okay, that makes a lot of sense. Thank you.
Cool.
Sorry for the taking up time.
No worries. So, I'm going to go back to Smith charts. This is not amazing looking, but hopefully you can at least see like the graph, even if you can't read the tiny words. Everybody okay with this? All right. So here's what we're going to do. If you saw my announcement, hopefully you at least downloaded the PDF of the Smith chart that I put up on our course website on Friday. If you didn't, take a second to go do that because you need one. You need a Smith chart for this. You can use a computer to do it, Or you can print one out. I prefer to print them out because it's easier to get your circles to be circles and stuff. But here we go. So this is going to be a little bit terrible because my kid broke my compass. So I have to do this the terrible way, but what are you going to do? All right, so this is a Smith chart. Sorry. And what it does is it maps the right-hand side of the complex plane. So that's all possible passive impedance values, right? So they have positive real part, and they could have imaginary part anywhere from minus infinity to positive infinity. And it maps that whole thing onto the unit circle. It also maps all the possible impedance values onto the associated values of the reflection coefficient, because the reflection coefficient is inside the unit circle. So this is a circle of radius 1 that represents reflection coefficient values. And then it has sort of projected and mapped onto it all of the possible values of impedance that get you each of those reflection coefficient values. And we do this, first of all, this works using the normalized impedance that is at the load of your transmission line. So here's how you do a normalized impedance. I'm gonna flip it over. So if I want to normalize an impedance, here's why we do it that way, right? The load reflection coefficient is ZL minus Z naught over ZL plus Z naught. But this has two variables in it. What if we just divided everything by Z naught? Then it would be ZL over Z naught minus 1 over ZL over Z naught plus 1. This thing here is the normalized load impedance. And for that, we use the little z L. That's why I'm putting the slash through the little z's, because now we have to distinguish between normalized impedances and real impedances. Even real is a fraught word here. So normalized impedances and non-normalized impedances, any of which might be complex. So here's what we do. A Smith chart. I'm going to orient you to the various things on the Smith chart first, and then we'll do a Smith chart problem, and then I'll have you do a Smith chart problem for the end of class. All right? So right across the middle of the Smith chart, this is the real line. This goes all the way from real part of impedance equals 0 over here on the left to real part of impedance equals infinity all the way on the right. The outside edge of the circle is the imaginary part of the impedance. It goes all the way from 0 to positive infinity. It goes all the way from 0 to negative infinity, all the way over there. You might notice that all of the infinite values land on the same point of reflection coefficient. That kind of makes sense, because whether you put in j infinity or minus j infinity, the reflection coefficient you get out is always 1. It's 1. The reflection coefficient on this circle is measured by the distance from the impedance point you chose. Like, say my normalized load impedance is, if I look at my real line and go out to 2 plus J1, and I pick this point, right? This is my imaginary part equals plus 1. I follow that line in. This is my real part equals 2. I follow that line up, find the point where they cross, just like plotting on a graph, except the graph is a little bit stretched. And that is little ZL equals 2 plus J1, or just 2 plus J. I can write that too. Then my reflection coefficient here, and this is where I wish I hadn't lost my compass and ruler. I was looking for them today and couldn't find them. Never have a 4-year-old. The reflection coefficient here is has magnitude equal to the distance between that load impedance point and the center of the Smith chart. And there's a scale down here at the bottom of the Smith chart. Let's see if I can zoom in a little further. So my reflection coefficient, E or I think this chart might be British because they use E for voltage, like Europeans use E for voltage instead of V. But you look at this scale for the linear reflection coefficient. This one is the power reflection coefficient, so that's like magnitude of gamma squared. You don't want that one. You want just the linear reflection coefficient, that's this one. And then you take the length of this with your compass, or by, if you're me and you are taking a senior elective in undergrad and you forgot to bring your compass to the exam, you just make a little mark on the edge of the paper there and measure the length of the reflection coefficient on this scale. Start from the center, where it's labeled center, and you get that the reflection coefficient magnitude associated with that load impedance is this much. Looks like 0.45. Whoops. It's from there to there. 0.45. See, here's my little piece of paper and the dots lining up. So now I know that my reflection coefficient is 0.45. And I can also find the phase of the reflection coefficient. But be careful with that because there are a lot of different scales around the outside of the Smith chart. So let's talk about what they all are. These can be in different orders on different Smith charts, so make sure that you read what the labels are. But in general, they all have wavelengths toward generator, which goes clockwise. So that is increasing the length of transmission line connected to your load. That's like if you have a transmission line connected to a load and you increase its length, you let it get longer, that means going clockwise around the Smith chart. So I can take a look at this and figure out what is the reflection coefficient at the load, and then I could figure out the input impedance too by rotating around the Smith chart and keeping the magnitude of the reflection coefficient the same. It does that thing with the two waves accumulating phase in different directions. It does that. There's also wavelengths toward load, which are away from the generator, and that would be counterclockwise. You use that one a lot less often. And then on the inside here, there are these two labels, angle of reflection coefficient in degrees and angle of transmission coefficient in degrees. The transmission coefficient is more useful if you're working with a 2-port or something, but in general, it is 1 plus gamma. If I want to know the angle of the reflection coefficient, though, all I do is draw a line through the center point and my load impedance point, and then I find out, I read the appropriate scale for angle of reflection coefficient in degrees, and I get, zooming in, this value looks to be about 22, 24, 26, let's say it's 27, angle 27 degrees. When you solve problems with a Smith chart, you tend to get magnitude and angle for your reflection coefficient values. So it's going to look like that. It might not be exact, but it's really good for visualizing stuff because here's the thing. Here is where A compass would be really handy. I'm just going to freehand a circle, and it's not going to be a very good circle. If I draw a circle of constant radius around this center point, what I get is all of the input impedance points for any possible length of transmission line that I might connect to this load. Right? This is called the constant reflection coefficient circle. Or it is when it has a constant radius. It is also the constant standing wave ratio circle, right? So this is the constant Viswar circle. It's the constant gamma circle. And if I want to know what the input impedance is looking into this line at some other length, if I start at the load, move around clockwise, and let that transmission line that's attached to it get longer and longer and longer, and then I read off the starting value here on the wavelengths toward generator. So my like L equals 0 point is actually here at 0.21 let's say it's 0.213. L equals 0 is about 0.213 wavelengths. And then let's say I want to attach a third of a wavelength transmission line to this thing. Well, I add 0.333 plus 0.213 and I get 0.546. Okay. Reflection coefficient repeats every half wavelength, so I'm only going to get as far as 0.5, and then I have to go another 0.046 on here. And that puts me at 0.042, 0.044, 0.046. It's going to be right here. And then if I want to find out what that input impedance is, I just draw a line between that line length and the center of the Smith chart, and look at the point where it intersects with my constant Viswar circle. If you are like me and you don't have a compass, you don't have to draw the constant Viswar circle, because you can draw this line first, measure this length, and then put this length onto that line. And it looks like my circle's a little bit off there, actually. So there you go. So I can use a Smith chart to figure out the input impedance to something. You want to see me do it? I'm going to say
Sure.
that, give me a load impedance. Just pick a value. It can be complex even. You type it in the chat. You can't be -1. But that's from the reflection coefficient time. Remember, it has to be a passive load. So give me 3 plus 2j. Okay, cool. It's already normalized, it looks like. So let's say that my normalized load impedance, little zl, equals 3 plus 2j. For people who are playing along at home and want to know what that would be in a non-normalized impedance value, we have to have some value for the line characteristic impedance. So I'm going to say that Z0 is 50 ohms, and that's a pretty common value. 75 is also a pretty common value, so are 100 and 300, but 50 ohms is what we're using today. That means that my non-normalized load impedance must be 150 plus J100 ohms to get 3 plus 2J. So first thing I'm going to do is follow my real line out from 0 all the way out to the part where it says 3. Okay, real part is 3. Imaginary part is 2. I gotta follow my imaginary axis all the way out until the point where it's 2. Imaginary part is 2, so I follow that in and find a place where the real part equals 3 circle intersects with my load impedance value is right here. Cool. Let's start by finding the reflection coefficient of this thing. Put my pencil right there at the center of the Smith chart. Line the sheet of paper or the ruler, if you're fancy, up with the impedance point. Did I get it? There we go. So I can read off the phase of the reflection coefficient immediately. Angle of reflection coefficient in degrees. It is the second scale out, and it looks like it is about 18 degrees. So I'm going to write it down right here. Gamma L equals some magnitude at an angle of 18 degrees. What's the magnitude? Do the same trick with my little piece of paper. Normally I'd measure this with my compass, but like I said, I lost it. Go down to the scale at the bottom. Find this scale that says reflection coefficient E or I. That means voltage or current. Measure it from the center, the point that's marked center with a little triangle on that scale. Make a little mark. And I get that the magnitude of my reflection coefficient, if I zoom in on my little mark right here, you can see it's between 0.6 and 0.7. That looks like about 0.63 to me. So then up here, I can write down that my load reflection coefficient is 0.63 at an angle of 18 degrees. All right, cool. Next, what if I wanted to know the input impedance to some transmission line that's terminated by this load? I'll even label it ZL here. How do I do that? Pick a transmission line length for me.
Um, 1.55. Like what are the units that we should?
In wavelengths.
Half wavelength.
Half wavelength is cheating because one time around the Smith chart is half a wavelength, so I get the same input impedance as the load. I don't even have to do anything if it's a half wavelength.
Well, that's easy.
Yeah, it's pretty easy. Actually, if you take a look at the wavelengths toward generator scale, it starts at 0, and you go all the way around, and the very last number, actually the last number is 0.49, but 0.5 lands right on top of 0. So because the reflection coefficient, remember the reflection coefficient is a function of position, gamma of L is equal to the load reflection coefficient times e to the minus 2j beta L. It accumulates phase twice as fast as the two waves individually. So the period of the reflection coefficient is half a wavelength on the line. And that's why going around the Smith chart once is only half a wavelength, not a full wavelength.
That's pretty cool. So how about 3/4 wavelength? Is that less easy?
Sure, 3/4 of a wavelength. Because of the half wavelength thing, I go fully around the Smith chart one time, right, from here all the way to here, and then I have to go an additional quarter wavelength. A quarter wavelength is halfway around the Smith chart. That's 180 degrees. So the easy way to do that is I don't even really have to measure, but if I did want to measure and it wasn't a quarter wavelength, I would look at this value here on wavelengths toward generator. I would notice that it is about 0.224 wavelengths, and now I would add another 0.25 to that 0.224, which would put me at 0.474. And I would find the point over here, 0.474, which is right about there. And then I would draw a line through the center of the Smith chart. Since it's a quarter wavelength, I can also just cheat and draw the line using the 2 points I already have and not measure. But I measured because it won't always be a quarter wavelength. All right, so I know what the phase of the reflection coefficient is going to be at that point, but I don't know what the input impedance is going to be yet. It's going to be somewhere around here. And we figure it out by measuring, again, this distance from the center of the Smith chart to our load impedance point, and then measure it along the new line that we made from the center of the Smith chart. And the point that we find there is the input impedance point. But it's normalized, so we have to unnormalize it. This looks like a value between 0.2 and 0.3 on the real line. It looks like it's 0.23. All right, so normalized Zn is 0.23. It is on the negative side, so minus j, and what's the imaginary part? That's 0.1, that's 0.2, it's less than 0.2, it's 0.18, 0.1, I'm going to say 0.16. J 0.16. And if I want to turn this into a not normalized input impedance, I have to multiply by 50 ohms. So 0.23 becomes 16, right? Or is it 1.6? Can't do things in my head anymore like I used to. 2.3 times 5, yeah, it's 16. No, it's not 16. 2.3 times 5, carry the 1, 5 times 2, 11.5, that's better. Yeah, 11.5 minus j.16, so minus j8 ohms. That is the input impedance a quarter wavelength away from this load that we made. That's how you do a Smith chart problem. Smith charts are a really useful conceptual tool, in addition to being a graphical tool that was historically used for solving transmission line problems, even though it's mostly not used like that anymore. I like them because this idea of the constant Visoire circle is really powerful. A lot of the time people use them as a thinking tool when they're talking about doing impedance matching problems to maximize the power delivered to a load. A lot of the time people use them to plot the impedance of a device like an antenna or something. And also they're just a good way to think about things. They have all of this graphical visualization stuff. So you can think about it as, well, the phase relationship between the two waves is always swirling around like this. The input impedance swirls around in the Smith chart. When it crosses the real line over here, that's always going to be a voltage minimum and a current maximum. When it crosses the real line over here, that's always going to be a voltage maximum and a current minimum. That's really how it works. When it crosses the real line over here, the value of normalized impedance that you read off for the input impedance is also equal to the standing wave ratio. Smith charts are crazy useful and super cool. They have all of this information embedded in them.
Excuse me.
Yeah.
For Zain, would you please explain the only the second part that you wrote, J 0.16? I kind of missed how you get that.
Oh, sure. So this was my Z-in point that I figured out by measuring this distance along the line that passed through the length that is a quarter wavelength away. So I measured a quarter wavelength around the outside of the Smith chart to this point, drew a line from the center through that point, and then I measured my constant reflection coefficient, same reflection coefficient over here, magnitude-wise, just a different phase. So then I could find that this is Zn. The real part I found by looking at the real line and following it down. And the imaginary part you can find by reading the markings off of the imaginary axis, which is the outside of the circle. So here I've got some value between 0.2 and 0.1. If you follow these lines in, these dark lines, you can see that's 0.2 and that's 0.1. But these are minus 0.2 and minus 0.1, right? So I've got minus 0.1, and there are 5 squares between minus 0.1 and minus 0.2. So that's minus 0.12, minus 0.14, minus 0.16. And that's where my line is. And so then I've got minus j 0.16. And then I multiply that by my characteristic impedance, which is 50 ohms. 0.16 times 50 gets me 8. So then I have minus J8 as the imaginary part of my input impedance.
Got it. Thank you.
No worries. We are out of time for it today, but the first thing that we're going to do next time is you are going to do an example using a Smith chart. So try to find some time before Wednesday to print at least one out. You probably will need like 5 because sometimes you make mistakes and want a new one or something, or maybe you'll do 2 problems. But I want you to get some practice using Smith charts to think about these things because they have a lot of useful information about them. You can also work them backwards. If you have the reflection coefficient, you can figure out what the load impedance is, or the input impedance and the length of the transmission line. You can figure out what things are. And you can do all this stuff using math too. But doing it with a Smith chart really helps solidify the behavior of transmission lines in your head. So we're going to do a lot of Smith chart problems to get this stuff to sink in. And that's going to be most of Wednesday. And with that, I think I'll wrap up. I am about half done grading those midterms. It's taken me a long time because the files all load slow, but I'm working on it. You can expect to see your grades pretty soon.